Well, we've spent the last couple of sections taking a look at different ways of visualizing solutions. And so, how do we visualize, how do we understand solutions without analytical methods, without being able to solve things directly? Because that's not always possible. And of course, there's this third option that we investigated in Chapter 1 where we use numerical methods. So we can use numerical methods. To estimate solutions or solution values at some future time based on a given initial condition. So this sounds familiar. This is kind of what we were doing in Chapter 1 when we were learning Euler's method. But this time we're actually going to be thinking about the phase plane and the extra dimension of time as well. And so that means we can think about our differential equations, our system of DEs, as a map. And it's a map on where to go to follow the path of a solution curve. And remember, for a system, this means which way and how fast. Because we're talking about vectors here. So it's not just what direction do we go, but how quickly do we move in that direction. So unlike what we've seen in Chapter 1, the numeric method, the Euler's method that we're going to be learning for this section, involves us doing things, thinking about which way to go, but also how fast to go. So if you recall from our previous experience with Euler's method, that Euler's method with a single equation allowed us to use the slope field to reorient ourselves. So we read the map and it said, okay, go this way when you're at that point, and then we went and followed that path, and it said, okay, now go that way, and we kind of followed it, and it made up a series of small little segments that sort of formed the curve. But for a system, the vector field stands in for the slope field. And our steps aren't actually on the graph itself. It's not so much that we're taking steps in one variable or the other. We're taking steps in time to extend the curve. So you can think of the Euler's method for a system as really being taking a look at the shadow of that three-dimensional curve, where when we move in time, you can see the extension of the curve, but it's not really this dimension or that dimension that represents our steps. So it's the same general idea, but just slightly complicated by the fact that we're in 3 dimensions instead of just 2. So Euler's method is pretty similar, and it's going to look pretty similar. You start with an initial condition. Now notice that is some initial condition assuming that t equals 0. So this is a point on the plane, the phase plane, when t equals 0. Now it doesn't have to equal 0, but we generally just refer to 0 time as our initial condition. And then we choose a step size, and notice the step size is delta t. It's how far we step in time. And then the next part of this is you step from one location on the phase plane to the next, and that's because you've increased the time by delta t. And so this is just a little ways away. Now it could be really far away or really close, depending on how big of a step that curve actually takes in that small amount of time. So we don't know. It could be really close. It could be nowhere near. It could be straight up above. It could be down below. It could be in any direction. We don't know. But we're going to be using the velocity vector, and that's the velocity vector is coming from our vector field. And moving along that distance, or a distance, I'll put it in quotes here because it's not really a distance, but a distance in the time dimension. And then we calculate a new velocity vector, take another step, wash, rinse, and repeat. You just keep doing that until you've either gotten to where you wanted to go or you've taken the number of steps that you wanted to take. So we're not going to get too far in the weeds on this. And by that, I mean, we're not going to do this by hand just because it takes forever to do that. So we're going to use Maple. And so notice it says as many times as are required, and that's whether you want to get to a specific t-value or you want to take a specific number of steps. So we're going to figure out how to do this in Maple. And in order to do that, we're going to make some sense out of a particular example on the next page. So let's take a look at the example that's on the next page. And as is usually the case in math, we start with something really simple. And if you remember from the last section, this looks an awful lot like one of those completely decoupled systems. Because it is. So not only is it completely decoupled, but this is one of those that we could look at and probably solve without much trouble. That differential equation in terms of x we know is going to have a solution that looks like this. X of t equals, well, that's exponential growth, so it's just c1 e to the t, 2t, forget about the 2. And then down here, this one is going to have a solution that looks like this. Y of t equals another constant times e to the t. So we know what the solution is already. So this is a known solution to us. So it's going to be useful because we're going to be able to compare our Euler's method to the actual solution. And that'll help us get a chance to see what's going on. And just as a reminder, we want to kind of verify that if this is the general form of the differential equation, we should be able to verify that this is a particular solution for the system. So notice it says verify, and just a reminder, this is just proving that the solution makes the differential equation true. That's what it means to verify. Literally, the word verify comes from the Latin for truth, right? So this equation, or excuse me, this matrix form of the solution, you could be written, if you wanted to, in parametric form, and it would just be the x of t solution, which is e to the 2t, comma, the y of t solution, which is just 3e to the t. So the question is this actually a solution for this system? And so we should be able to prove it. And I'm actually going to do it using the matrix form, just to give us a little bit of practice to see how this works. So written in matrix form, this system, our system in matrix form, would look like this. We'd have our take the derivative with respect to time of some solution, which we'll call capital Y, and we'll let this be y1 right there. So we should be able to show that if we take the derivative of that, derivative of x and y, that should be equal to 2x on top and y on bottom. That must be true. So what's our solution? Well, our solution, y1, is this thing right here. So that means we're going to be taking the derivative. Let me scoot this up a little bit. We're going to be taking the derivative with respect to time of e to the 2t up there and 3e to the t down below. And that's got to be equal to what we get when we plug in 2 times our x. So that's going to be 2 times e to the 2t. And in the bottom, it's got to be equal to our y, which is just 3e to the t. So the question is, are those two sides in fact equal? If they are, then this thing really is a particular solution. So on this side, we're going to take the derivative of this matrix, and it seems like it would be really complicated, but all you do is apply the derivative operator to the top element and then apply it to the bottom element. So this on the top is, well, the 2 comes down out front, so you'd have 2e to the 2t. And in the bottom, the derivative of 3e to the t is just 3e to the t. No big shakes on that side. The question is that the same thing as what we have over here, which of course is 2e to the 2t, and on the bottom, 3e to the t. So we just proved, since these two things are identical, we just verified that this really is a solution. So we can say that thing, that y1, that matrix, is a particular solution. So, yay! Okay, so what we're going to do now is we're going to kind of wipe our brains and pretend like we didn't know that this was a particular solution. Pretend like we didn't know that, because we're going to be using this later on to check our answer. But can we use Euler's method to approximate this solution? So down below, I'm just going to say, pretend we didn't know this. Can we use Euler's method to approximate? And that's what we're going to do on the next page. So I'm going to stop the video here just so that so that the videos aren't super long. But on the next page, we're going to jump right in and figure out Euler's method, and that's going to involve using a little bit of Maple as well. So make sure you've got your Maple handy and can follow along in Maple as well.